Okay, I'm giving another lecture here on partial differentiation and some geometrical interpretations. I'm going to talk a little bit about tangent planes to smooth surfaces also. Okay, in this particular drawing that I've got some sort of smooth surface. Okay, we'll be more precise about what that actually means ultimately. But just go ahead and think about it this way right now. A surface is going to be smooth if there's a well-defined tangent plane at each point on the surface, okay? Not just a tangent line, a tangent plane. We're dealing in higher dimensions now, aren't we? Okay, again, we'll say more precisely what that actually means here, but use your intuition for now. Now, right now, just to explain some more with our partial derivatives here, you can see in gray that I've got some sort of smooth-looking surface. And here I'm cutting that surface by what? By a plane where y is fixed. In fact, it looks like y equals 0 right here. Okay, do you see that right here? Y equals 0. Okay, so this is the plane y equals 0. And it's cutting this surface. This surface passes a vertical line test in the sense that every line perpendicular or orthogonal to the xy plane intersects the graph, or the surface, I should say, which is the graph, at most one point. So this looks something like this. Z is a function of x and y. So for each xy value, you just get one z value coming out of it. Okay? But anyways, that nice smooth-looking surface is cut by this plane here, and what you get here, do you see what you end up getting here? I'll draw with the red line over the green now. Do you see you got a nice smooth looking curve? Okay, that's actually part of the surface. Okay, it's the intersection of the green plane and the gray surface. Okay, now you can talk about it at a particular point on that curve that also lies in that plane there. Okay, do you see that what I've drawn here is actually what? A line. Okay, what I've actually drawn is a line through that curve that's embedded within that plane y equals 0. Okay, so that's what that black line is. Now that black line is going to have a particular slope, right? Okay, it's going to have a particular slope. Now, this is when y equals 0 here. Now the slope is going to be rise over run. The rise is going to be a change in what? The z direction. But what? The run is going to be what? A change in the x direction. Okay? So this is going to have a particular slope. This is actually going to be the partial derivative of f, or z if you wish. Since z is a function of x and y, we'll just say it's f here, right? This is the partial derivative of f with respect to x. Y is being held constant. Here, this is at the point what? I don't know. Y is 0. I don't know what the x value is. Okay, maybe the x value is 2 or something like that. Okay, do you get the idea of what this is? Okay, now generally this is going to be a function of both x and y. It's going to depend on the particular x and y value you're talking about on the surface. But the partial derivative of f with respect to x is going to be the slope of the tangent line to the curve that is formed when what? The plane y equals constant, whatever that constant is, intersects that smooth surface at a point. Okay? We can get some more visuals in on this that are maybe even a little bit better. Okay, here's some other ones. Does this give you the idea? Okay, I don't know if you can see this. It's kind of blurry. This is actually the x-axis, and this is the y-axis. These should actually be turned around. This should actually be the x-axis, and this should be the y-axis. Okay. Okay, so that's the x-axis and the y-axis, and the z-axis up here for the positive z-axis. Okay, let me put that in there. Okay. Now I've got some what? Surface z equals f of xy. Okay. Now I'm talking about at a particular point on the surface, That point is here called P. Okay? P has a particular value of x and y. Okay? It looks like the x value might be what? Let's say the x value is little a, and the y value is b. The z value would be what? The function evaluated at a and b. Okay, so this would be f of a, b up here. That would be the coordinates of this point. Now, if I have a particular plane here, let's talk about the partial derivative of f with respect to x at a, b. What would that mean? Well, what's being held constant here? Well, the two independent variables are x and y, so you're holding y constant. So graphically, what we do is imagine what? The plane y equals b intersecting the surface, and we get what? We get this curve here from C to D, okay, from point C to D. Do you see the curve here? I didn't want to draw too much on it. I'll probably muff it up here. And then you can imagine a tangent line to that curve at P. What's the slope of the tangent line to that curve? Okay, that would be this value right here, the partial derivative of f with respect to x evaluated at the point AB. Okay, all right, it's dependent upon the points A and B. So that would be the slope of this tangent line right here. Does that make sense? Okay, what would be the slope of this tangent line right here? That would be what? Well, you can see here that what? X is being held constant, so that you can imagine the plane x equals a intersecting that smooth surface. Okay, and you get this nice smooth curve from A to B. Okay, and it has a tangent line at the point B. The slope of that tangent line is what? Okay, so it actually looks like it would be a negative value if this is the origin, because what? It looks like what? The value of z is decreasing as y gets larger here. But anyways, it's going to be the slope of the tangent line to that curve, partial derivative of f with respect to y, because x is being held constant, and that's going to be a number, some value, at the point AB, or if you want, the point ABC, where C is the function evaluated at A and B. But it's only dependent upon what actually goes into the calculation here is A and B, right? So this would be evaluated at AB, and that will give you the slope of this line right here, okay? This one, this second one, okay? Does that make sense? Okay, so you understand partial derivatives? Okay, here's a really nice one here, really nice drawing, okay? I've got some nice smooth surface here where z is a function of x and y. Okay, it looks like here. And I've got a point instead of AB, we've got it labeled x naught, y naught. Okay, and you could talk about what? Do you notice in this drawing, though, we've got what? Tangent vectors here. Okay, and so instead of just lines, we've also got vectors drawn here. But we've got what? Tangent 1. This is where y is being held constant, you can see, where y is equal to y naught. Okay, so you could talk about the slope of the tangent line to that curve right here. You can see the purpley looking curve. There's the tangent line T1. It has a certain slope. Okay, that would be the partial derivative of the function f, or z if you wish, evaluated at the point x naught, y naught. And likewise, T2 is the tangent line to the curve at the point P. There, x is being held constant, so that's what? The partial derivative of f with respect to y. Okay, so we've got z as a function of x and y again, we'll say here. Okay, so you understand these. And now these are written also as vectors, okay, parallel to those lines. Okay, vectors parallel to those lines. Okay, now this is a nice smooth curve, and we're just going to bring in here the idea that if I've got a normal to the surface, which I'm calling n here, Okay, these are boldface, but the way we draw them, we usually put bars on top because I can't draw boldface. Those are bars on top, but those are vectors. N, which you could consider V cross, it looks like V2 cross V1 maybe. That's going to give you what? A normal vector to the surface at this point. That would be normal to the tangent plane to the surface at that point P. Okay? In fact, that's what we said. The differentiability of this function actually means that there's a well-defined tangent plane at each point on the surface of z equals f of xy. That's what that means here. Now we're jumping the gun just a bit here, but I'm telling you what's ahead here. Okay, so we're going to find a couple tangent vectors, and if we take their cross product, we're going to have a normal. That'll be a normal for the tangent plane, and then we've got a point on that plane being the point P, and we can actually find the equation of the tangent plane. So I'm jumping ahead a little bit, but I'm going to show you what's ahead here. Now I called this lecture 29 here on partial differentiation. Suppose, let's take a couple examples here just quickly. Z is a function of x and y. It's x to the y power, okay? All right, so we're going to take values of x that are somewhat restricted, say x is positive here. We don't have any weird complex values. What's the partial derivative of z with respect to x, which is the partial derivative of f with respect to x, which also has this subscript notation, okay? So you should have read or seen about this in a previous lecture. F sub x, that means what? The partial derivative of f with respect to x. Okay, this particular symbol is what we call nabla, okay? Or some people call del, okay? It's a funny backwards looking 2 kind of thing, but it's supposed to be a weird deformed D, okay? But this is the partial derivative of the function with respect to x. So what we're going to do here is imagine that what? Y is held as a constant, and then we're going to take its derivative with respect to x. And you can see here from calculus 1, you would just use the power rule. So it would be y times x to the y minus 1 power. Likewise, if we were to go partial of z with respect to y, notice it's the subscript here. Okay, what are we doing there? We're going to go ahead and let x be held as a constant, and we're differentiating with respect to the exponent. Do you remember that? Some students tend to forget this. How do you differentiate that? Okay, where the base is being held as a constant. The answer is it's x to the y times the natural logarithm of the base. Okay, so don't forget this in case this appears on an exam or something. Okay, so there I've calculated a couple partial derivatives for you. Let's do it again here. There's also another chain rule type property I want to emphasize here. Suppose z is f of xy is the natural logarithm of the square root of 4x squared plus 10y squared. Notice that I can go ahead and bring out the half out front as a power, right? Because the square root is just raising the radicand to the half power. So I can talk about 1/2 the natural logarithm of the sum of the squares here. That's always going to be non-negative, okay, here. What if I'm going to take the partial derivative of f with respect to x? Here's what you're going to do. You're going to go ahead and, well, half is going to be carried as what? Just a scalar multiple here. But you're going to go ahead and treat this as a single variable. You're going to go ahead and differentiate that with respect to that variable. Imagine that being z or w or something. And you would get what? The reciprocal of that function, which I've got here. But don't forget the chain rule type step here, where what you want to do is multiply by the derivative of the inner function, right? In any sort of composition like we have here, natural logarithm composed with this function, multiply by the derivative of the inner function. In this case, it's just a partial derivative, though. So you're holding y as a constant when you take the partial derivative. So the partial derivative with respect to x of 4x squared plus 10y squared is just going to be 8x, because the 10y squared is acting like a constant, and therefore when differentiated with respect to x yields a 0. So we just get what? 8x up on top. Don't forget your half. The whole kit and caboodle becomes what? 4x over 4x squared plus 10y squared. Okay, likewise, you're going to do the same thing here, only differentiating with respect to y. So f sub y, And that's going to be what? 1/2 differentiate with respect to y this time, holding x as a constant. And you see that what you're going to end up with there is what? 20y. Okay? But you're going to be taking half of that again, so you'll get 10y on top. The denominator, once again, will be the 4x squared plus 10y squared. Okay, so I hope you understood that one. Okay. Okay, I'm going to do something real quick here. Suppose z is a function of x and y is 3x squared minus xy plus 5y squared. This is a nice polynomial function. It's not only continuous everywhere, it's also going to be smooth everywhere, so it's going to have a well-defined tangent plane everywhere. Find z, first of all, if x is 1 and y is 2. Okay, simple evaluation. You just plug in those values here. And I found the function f at 1, 2 was 21. Okay, now find f sub x at 1, 2. Okay, where x is 1, y is 2, in other words. Let's go ahead and calculate f sub x. F sub x would be what? 6x minus y, because what? Y is being held as a constant. Differentiating with respect to x, we would just get 6x minus y. Plugging in the numbers 1, 2, we would get 6 minus 2 is 4. Okay. Find f sub y at 1, 2. Okay, so differentiate with respect to y. We would get 0 for the first term. X is acting as a constant, so we would get negative x plus 10y. Yep, negative x plus 10y. Evaluate at 1, 2, we get negative 1 plus 20, we get 19. Okay, so these are instantaneous rates of change in the x direction and the y direction. Okay, now I'm going to ask you to find tangent vectors to the surface at the point 1, 2, 21. Okay, the 21, of course, comes from what? From this right up here. Okay, so I've got the x, y, and the z values written here. What I'm doing is considering a situation like this. I want a vector 1 and a vector 2 here. Okay? So let's come down here. Okay? What would be a vector 1? How about this? 1, 0, 4. Where'd my line go there? Okay? 1, 0, 4. Notice that I've got what? One change in the x direction, that's I, right? No change in the y direction, and then a 4-unit change in the z direction. Okay? I got a 4-unit change because of this right here. So this is actually would be a tangent vector. So this is what I'm calling T1 here. Okay? How about a T2 vector? No change in the x direction, 1-unit change in the y direction, so that's J, and 19-unit change in the z direction because of what? The slope here. Okay, the f sub y at 1, 2 was actually 19. So this is going to be, these are going to be two tangent vectors at this point 1, 2, 21. So that I've got these two vectors, and this is the, in general, what you can do. You can go 1, 0, f sub x, 0, 1, f sub y. You're going to, now don't leave these as functions. You've got to do what? You have to evaluate these at a point to actually get numbers out of these, like I did up here. Okay? Those are going to be tangent vectors always, but remember, you're going to be substituting numbers in to do what I'm about to do, which is to get a tangent plane. Call the Cartesian form of the plane. I also call that the normal form, if you'd rather do that. Okay, so I'm about to find a normal for this. Okay, for this plane. Now I'm jumping the gun. I'm not even showing you. I haven't proved that it has a well-defined tangent plane at every point. But if it does, this is going to be it. Okay, this is going to be it. And in fact, it does, and this is the function. This is going to be the plane that we're looking at. Okay, let's just take the cross product in either order. It doesn't matter which. It'd be pointing up or down. Okay, I went T1 cross T2, and I've got this vector. Okay, all right, very easy. Can you do this in general, by the way? 1, 0, f sub x, 0, 1, f sub y. Yeah. Okay. Okay, so I've got that vector. Okay, and then I'm going to do what? Dot it with what? the difference vector from 1 to 21 to an arbitrary point x, y, z on the plane. So I've got x minus 1, y minus 2, z minus 21, dotted with the normal ought to give you what? 0, because these are supposed to be orthogonal all the time, right? Okay, these two vectors will be orthogonal all the time. And then I just rewrote it a little bit, so I've got z equals 21 plus 4 times x minus 1 plus 19x minus 2. Now I want you to focus on that for a second. Where did the 21 come from? Okay, where did the 21 come from? Well, you know it came from what? There. Yeah, that's the value of the function at 21. Now I'm writing this in a slightly non-standard way. Okay, I'm calling this normal form, but I haven't actually multiplied the 4 onto the x minus 1 here. Why am I going x minus 1 here? Well, what point are we looking at? We're looking at the point 1, 2, 21. Okay, so now you see where the 1's coming from, where the 2's coming from here, right? How about the 4 and the 19? Where have you seen those numbers? Oh, where'd those come from? Oh ho, these came from these slopes, right? These partial derivatives, 4 and 19. Okay? Alrighty, so do you see where everything came from? Now I could multiply it out in greater detail, but I'm trying to illustrate something here. Okay? Do you remember tangent lines in Calculus 1, how they look like? Through the point x1, y1, with slope m equals f prime at x1. What would it look like? It would be y equals y1 plus m times x minus x1, or x sub 1. Okay? Does that make sense? Okay? How about tangent planes in Calculus 2? It's going to be what? Z equals z1 plus m1 x minus x1 plus m2, a different slope, y minus y1. What are these different slopes? Well, this is going to be what? The slope here and slope here are going to be those partial derivatives with respect to x and y, respectively, evaluated at the point x1, y1. I guess I called it x1, y1. I should have said x naught, y naught, but I'm looking at this situation. I'm finding the equation of that tangent plane. Okay? The equation of that tangent plane. Okay? Do you see how they mirror each other? This is exactly what's going to be happening in Calculus 3. Okay? Now, let me emphasize here, if you're using this form, you've got to have this. Z is a function of x and y, explicitly a function of x and y. We're going to have other cases where z is a function of x and y only implicitly. There you're looking at cap of x, y, z equals a constant. Okay? So that's going to be what we would call a level surface. That's something else. Okay? We're going to use a slightly different formulation. Okay? Well, anyways, I hope you understood that. I'm jumping the gun a little bit, but I'm showing you what's ahead here, and I'm showing you that it's really not that hard. Okay? All right. I hope you understood.